Welcome to MEM09011 Apply Basic Engineering Design Concepts. This lecture is a supplement to student workbook and other resources made available to you. Make sure you access your participants' workbook, as this will be invaluable for completing the online quiz and practical activities. For those of you who don't have access to Microsoft Office, LibreOffice is a free, no strings attached, complete Office suite. This will enable you to create documents, edit photos, create PDF files, and edit PDF files. There's a link to the download location on MEM09011. Good references and textbooks are invaluable to becoming a professional engineering tradesperson. Here's a great publication, Hydraulics and Pneumatics, covers the subject quite well in plain English. It's available for purchase from Amazon, or you can download a PDF version off the net somewhere. Just a reminder, check MEM09011 regularly for updates and new resources. Just a reminder that MEM09011 is available on your mobile device. You can download the app from your favorite app store. All the SWIMS documents and work instructions, risk assessments, data sheets used in this lecture are available from pConnect. All the parts references in this lecture were downloaded from pertech.com.au. Think, plan, do, review, make working smart a part of your day-to-day routine. Before we begin, let's look at some motivation. The success paradox. Is success luck or hard work, or a combination of both, or neither? Is success just based on hard work? Or is it just a myth? Let's have a closer look. Hard work. Here's another bias, egocentric bias. This basically means that you trivialize everybody else's contribution and assume that you did all the work, so you deserve all the spoils. It's easy to overlook or forget the circumstances or the people that helped us get to where we are today. What if hard work had nothing to do with it, just in the right place at the right time? Let's look at an example. Here we have 12 people who were randomly put into teams of 4, and a random team leader was assigned. They were given a brainstorming activity and each had to contribute one idea. At the end of the exercise, each team leader was given 5 cans of beer to distribute as they saw fit. The experiment was run multiple times, and it was found that in 80% of the times, the team leaders kept their extra can of beer for themselves. Even though their contribution was the same as everybody else's, they deemed their position as a team leader warranted the extra reward. Let's not hate the team leader. Each team member was pulled aside and asked what they thought their contribution to the project was. On average, they claimed that it was 70 to 80%. Big egos get things done. Egocentric bias can be a useful delusion. Believing that your hard work is paying off can keep you motivated. Here's another bias that can be attributed to hard work and luck. It's attribution bias. Basically taking the credit for all the work. For example, how many of you can name one of the 400,000 people that worked on the Apollo mission to get Neil Armstrong to the moon? We all remember Neil Armstrong's name, but can anybody name any of the 400,000 people that got him there? As with the Manhattan Project, everybody knows the name Oppenheimer, but forgets about the 2,000 physicists that worked with him to get that nuclear bomb built. I doubt very much that he was the smartest person on that project, but another example of attribution bias. Is success purely luck? Were we just born in the right place at the right time? Or did we just get lucky and meet the right person? We already looked at being in the right place at the right time. Imagine if Albert Einstein was born in Burundi, for example, where the average yearly salary was $750. I think he'd have other issues like surviving. I don't think he would have much time to develop his general relativity and special relativity theories. And regarding attribution bias, don't forget Albert Einstein had an army of mathematicians and physicists assisting him also. I think hard work and luck do play a part, but I like to think of it as serendipity. It's basically opportunities that present themselves merely by going about our day-to-day activities, or giving things a go, or trying things. I use this analogy a fair bit for serendipity. It's like finding $5 on the road while walking to work. There's a mixture of work and luck. You wouldn't have found the $5 if you hadn't been going to work. Serendipity. In a previous unit, we looked at the stamped analysis and the 10-step hose manufacturing process. In that unit, we looked at how to manufacture a hose from an existing sample. But what about if we have to manufacture a hose from a specification or there's information missing? This is where we use basic engineering design concepts to get the information that we need. Here's the scenario. We have been contacted by a mechanic who inherited a log splitter service job. The previous mechanic has disappeared with one of the hoses and some of the adapters. We've been asked to manufacture a replacement hose assembly. To design and manufacture a replacement hose, we need to ask some questions. Step 1, what is it? Step 2, how does it work? Step 3, what are the constraints? Where is it going to be used? How big is it? Step 4, how many of these hoses do I have to manufacture? Step 5, how long does it have to last for? Why didn't it last so long? And step 6, how do I test the item and make sure it's fit for purpose? Let's look at step 1. What is it? It's a portable hydraulic log splitter, and the hydraulic pump is powered by a 4-stroke petrol motor. It is important to understand how the log splitter works so we can make informed decisions on its hose manufacture. The mechanic sent me a hydraulic circuit diagram, and now we'll have a closer look. The circuit consists of a cylinder, directional control valve, pump of course, and we have a pressure relief valve. Doesn't seem to be any metering on the retraction and extension of the cylinder. It's pretty simple, basic circuit. Here we can see the directional control valve positioned to extend the ram. 3. What are the constraints? Well, it's portable, petrol-driven pump, and it's a harsh environment. How many do I need? It's not a production run. I'm only making one hose, so I don't have to worry about tooling up for mass production. How long does it have to last for? What types of hoses and materials do I use to manufacture the hose assembly? Why was the other one removed? Was it faulty? What caused the fault? How do I test the item? This is going to be going out to a remote location. We'll need to make sure that the hose is fit for purpose before it leaves to the customer. Part of the design process involves collecting information. The customer advises that we have 2 adapters, 1 hose assembly missing off the log splitter. Part of the design process means that we have to be organized and work systematically. Here, I've created a template to start populating the information that we need. On the right is the known data. This is the information that the mechanic gave me. It said the system was stamped 200 bar system pressure. There was a 50 litre a minute sticker on the pump. And the manifold thread for the cylinder and for the directional control valve, the thread sizes were luckily stamped on the units. So I managed to get that information. On the bottom left of my sheet will be my bill of materials, all the parts I need to collect to create the replacement hose. Known data. First thing I need to do is find out the flow velocity so I can work out the hose diameter. In this example, I'll be using a nomograph to work out the hose bore and the pressure. In a later unit, we'll be using mathematical formulas and equations to calculate the same thing. What information do we have? Well, let's look on the left. Our pump is delivering 50 litres a minute, and we know going to the right that we are replacing a pressure line. Let's draw some lines from the flow rate to the flow velocity and see if we can get any of those intersecting points to line up with a dash size or a bore size. And yes, it's a dash 12. And we also managed to derive a flow velocity, which is 4.2 meters per second. According to my Pertec catalogue, a dash 12 is a 3/4 inch hose bore ID. Okay, let's add our flow velocity and hose ID to our known data sheet. I rang the customer back. They forgot to give me a hose length, and he's given me a value of center to center of the port, size of 800 millimeters. To work out my hose cutoff length, I'm going to need to know what hose adapters I'm going to be using, as per our Pertec 10-step hose manufacturing procedure. The mechanic has requested that I use JIC fittings when possible. Let's look at adapter number 1. It's a female internal thread on the cylinder. It's a UNO 1 1/16 inch 12 TPI thread. I need to collect a fair bit of information, so I'm going to use a template to make sure that I keep track of all the information that I'm collecting. According to my Pertec thread identification booklet, my 1 1/16 inch 12 TPI is a Pertec -17. Let's start populating the side 1 of our adapter. 1, template, 27 millimeter diameter, 12 TPI, UNO, and it's a -17. A quick reference to my Pertec adapter identification table. We're looking like a JIC -17 for the other end. As we can see, the ID/OD dimensions for JIC and UNO are pretty close. Let's start populating side 2, diameter 27, angle JIC 37 degrees, 12 threads per inch, and it just happens to be a -17 also. According to my Pertec adapter chart, it's a type J, UNO to JIC, male to male. Perfect. Adapter 1 is a J-17-17. A quick check to the Pertec catalogue. Perfect. Let's add the adapter 1 part number to our bill of material, which is a J-17-17. Now let's have a look at adapter 2. What information do we have? It's a BSPP to JIC. The internal thread on the directional control valve manifold is a BSPP 1 inch by 11 TPI. Let's create a identification table for adapter number 2 using our template. According to my Pertec identification booklet, a 1 inch 11 TPI BSPP thread is a -16. Let's populate all the information that we have for side 1 on adapter 2. Quickly check that on my Pertec adapter identification table, -16, perfect. I'll pick a JIC thread for the other end, as specified by the mechanic. I'll keep it at -17 because the ID is still bigger than the hose diameter, so we won't introduce any interference or turbulence. Let's populate the table for adapter 2, side 2, and we have a -17 JIC. BSPP to JIC, male to male, looks like it's a type C. Let's complete our adapter identification table, and side 2 is populated. A quick check to the Pertec catalogue, C-16-17, perfect. Let's add that second adapter to our bill of materials. Now let's have a look at our hose tails. Let's grab our hose tail identification template. This will make our life a little easier. We will be using a 90-degree JIC hose tail, so we're a JF9. JIC female 9. Configuration, JIC female, JF. Angle, 90 degrees. Fitting size, -17. Hose size from a nomograph, -12. Series adapter, I'm going to have to go to the hose identification chart to get this information. After looking through the options in the catalogue, I come across R2AT. It seems to meet all my criteria for pressure and temperature and environment, and I have it in stock. Let's have a quick check of the catalogue. 3/4 ID, 3/4 of an inch ID in the bore, perfect. Maximum working pressure in bar, 207. My specification is 200, so we're good there. Let's quickly check some of the other parameters. Hose tail specifications. Looks like I'm a Series J, 3/4 inch or above. Temperature ratings, minus 40 degrees Celsius, 150 degrees Celsius, perfect. Safety factor, 4:1. Application, medium to high pressure. Good. And specifications conforms to SAE standards. Perfect. Let's add my hose spec to my bill of materials. R2AT HT-12. I can now complete my hose tail template, and we know that it's a J series because it's 3/4 inch to 2 inch. A quick check on the catalogue for the hose tail adapter. Perfect. All we need now is our hose cut length. I have added the hose tail part numbers to my bill of material. 3 and 4 are exactly the same, so they're the same part number. The measured length of the hose is 800 millimeters. The A dimension of our hose tails is 55.50 millimeters. So 2 times 55.50 millimeters is 111 millimeters. Our cutoff allowance is 111 millimeters. Therefore, our cutoff length is 800 millimeters, which is our measured length, minus 111 millimeters, which is our cutoff allowance, gives us a cutoff length of 689 millimeters. When hydraulic hoses are pressurized, they actually get a little bit shorter, at about 5% to the hose length to compensate for this. 689 millimeter cutoff length plus 5% to compensate for the hose shortening when it gets pressurized is 723.5 millimeters. And just a reminder that the tail ends will grow a little bit in length after you crimp them. So crimp one end, measure, and then adjust the length on the other end. Let's add our cutoff length for our hose to our known data, which is 723.5 millimeters. Review your learning manual for the 10-step hose manufacturing procedure. Hose tail templates can be downloaded from MEM09011. Adapter identification templates can also be downloaded from MEM09011.